This is a project that I worked on years ago, a church in Albany, New York. It was a good representation of what had happened there. In an energy savings project, the parish actually installed interior insulation and drywall over the masonry walls on the north elevation. And once that happened, the wall started falling apart pretty rapidly within a few years. And the other elevations where they didn't put the insulation in were unaffected. And so this is, when I took this apart, you can see this terrible picture because it's scanned from an old photo. There's some rigid insulation here, extruded polystyrene, good vapor barrier, and then the brick is starting to spall. This is a view from the interior. So the important thing to keep in mind here is, that wall has been leaking forever and a day. It's got all kinds of masonry joints, mortar joints. It didn't have any flashing. The conditions were just ripe for it to deteriorate. And what happened was the insulation just makes it happen more rapidly. Right? So we have a lot of these buildings, and once we put insulation in there, we just accelerate the pace of some of these deleterious mechanisms. One of the things that Woofy allows you to do is to introduce water leakage. Right? That's sort of one of the pieces in the engine that you can use. You can the water leakage, I think, works as a percentage of the water that actually hits the exterior wall. And when you put that in there, not surprisingly, you get a lot more water content. This again is more of a qualitative tool, because how is a person to estimate how much water leaks into the wall, right? But it allows you again to look at how different configurations that you might consider respond to being stressed by water penetration. That's really the only benefit that I see. I think the way the engine works, and maybe you want to pipe up on that, it is that Woofy derives from the weather data and the height of the building and the orientation. It derives some sort of water amount that hits the exterior facade, right? And it just takes 1% of that amount and says, all right, go in. And I think that's how that works, which is, of course, highly unscientific, but again, useful for relative comparison. Okay, you say, so what, right? Maybe we'll deal with the freeze thaw, right? We can do some testing to determine whether our brick is actually durable. And there's cyclic freeze thaw testing that you can do in the lab. It takes a couple months. You can also go about determining the durability in a more roundabout way with laboratory analysis and look at other parameters of durability like compressive strength and water absorption, and look at the pore structure. But at the end of the day, you still don't know, right, for a historic brick. And I really don't like that method, and just want to impress upon you the most reliable method to avoid freeze thaw damage is still to reduce the water content of the masonry, which is, of course, a truism in all of engineering, right, and science. If you can get the demand reduced, you're a lot better off than trying to increase supply. To summarize, thermal considerations for mass masonry walls. Thermal performance is typically modest by contemporary standards, but rehabilitation options such as adding insulation must be considered carefully to avoid increased risk of freeze thaw damage. Right? And particularly introduction of the vapor barrier may increase the condensation risk. You can use hygrothermal analysis to determine the risk of moisture accumulation, thermal analysis to look at the R value, but then lasting, you can read this, but good old masonry waterproofing work is still required. Try to keep the water up. Humidification, we're frequently called upon to look at building envelopes that the owners are desirous to add humidification to the building, to ask, what's going to happen? What can you do for us here? And there's really two basic reasons to humidify buildings: occupant comfort, to increase the relative humidity during the winter, but we hear that's on its way out, fortunately. And really the more typical driving factor to add humidity to a historic building is preservation of artwork and artifacts. Curators like to see 50% relative humidity with very close tolerances. And again, you can use some modeling tools to look at the water content of brick masonry at 30% relative humidity and 50% relative humidity, and not surprisingly, you get some uptake of moisture there. Adding humidification to solid masonry buildings. If you have a thick enough masonry wall, frequently the thermal performance of it is sufficient to sustain some level of elevated humidity without causing condensation. And that's why it's important to run these analyses. But if you have 70 degrees Fahrenheit, 50% RH, and a dew point of 51, and at 0 degrees outside, 70 degrees inside, the dew point may just stay sufficiently high to avoid condensation under most conditions. Right? I mean, I don't think anybody would be shocked in a historic building if you get condensation once every 5 years or once possibly once every year, but it stays sufficiently high until you hang something off the wall, right? And there's that exciting paper that that lady at the Smithsonian wrote, right, where they put the pictures on the wall and it started condensing behind it. Once you hang something on the wall, right, you keep beneficial heat from getting to that wall, and you drop the surface temperature behind the picture to 44 degrees, and then you get condensation. And one of the ways to deal with that, and we've done, I think, 2 or 3 projects like this, is to hang the artwork on a separate interior finished wall that you then turn into a return air plenum by hooking it up to your return air and then drawing air through here. That way you have positive pressure, which curators like. You have negative pressure behind here, which building envelope folks like, because you're not pushing humidified air into the building envelope. And the conditions are the same on the front and the back of the wall. Now, all this, of course, is predicated on the notion that even without all this, right, the wall still must have sufficient R value to not condense under those conditions. And here's this picture of how that works. Is a photo of the connection to the ductwork. Then there's some air inlets at the base of the wall. And I think this is the, trying to remember where this is, the Mead Out Museum, I think at Amherst, where they, this hidden sort of in the baseboard. And that works pretty well if you can sustain this kind of substantial intervention, right, which you may not be able to with most of your historic buildings. Your hands are just tied.